Section 3.1 Vectored Value Functions and Space Curves. So let's start off with the definition of a vectored value function. Our first step in studying the calculus of vector value functions is to define what exactly a vector value function is. We can then look at graphs of vector value functions and see how they define curves in both 2 and 3 dimensions. So let's begin with the definition. A vector value function is a function of the form r of t equals f of ti plus g of tj, or in 3 dimensions, r of t equals f of ti plus g of tj plus h of tk, where the component functions f, g, and h are real valued functions of a parameter t, and vector value functions are also written in the form of r of t equals f of t comma g of t, or r of t equals f of t comma g of t comma h of t. In both cases, the first form of the function defines a two-dimensional vector value function. The second form describes a three-dimensional vector value function. Just a quick note, the parameter t can lie between two real numbers, whatever it's bounded by. Another possibility is that the value of t might take on real numbers. Last, the component functions themselves may have domain restrictions that enforce restrictions on the value of t. We often use t as a parameter because t can represent time. So the restrictions that you'll often see are those trig functions where they're undefined. So think of your reciprocal functions where tangent's undefined and like cosecant, secant, and cotangent. Those values that may produce an undefined value, those are most likely going to cause a change in your domain. So let's take a look at this example. For each of the following vector value functions, evaluate r of 0, r of pi over 2, r of 2 pi over 3. Do any of these functions have domain restrictions? All right, so let's go ahead and work on A. So for A, we're given r of t equals 4 cosine ti plus 3 sine tj. Okay, so we're just going to treat this as maybe a function. Think back of your algebra days and just input that value in for t. So plug in for t. So first we have r of 0 for our first function a. So we're going to plug in that number for t. So I have 4 cosine of 0 I plus 3 sine of 0 j. And of course, having a unit circle makes it super helpful. That way you don't have to scramble around punching numbers in your calculator. So cosine at 0, that's 1. So I have 4 times 1i plus sine at 0 is 0, 3 times 0, j. Well, anything times 0 is 0, so we're just left with 4i plus 0j, which is just 4i. All right, next one, we want to evaluate for r of pi over 2. So we just go ahead and plug in pi over 2. So I have 4 cosine pi over 2 I plus 3 sine pi over 2 j. All right, work it out. 4 times cosine at pi over 2, that gives us 0 I plus 3 times sine at pi over 2, that gives us 1 j. So we're left with 0i plus 3j, which just gives us, in return, 3j. And lastly, r of 3 pi over 2. No, 2 pi over 3. I said that backwards. Or I said that reciprocally, if that's a word. All right, so I have 4 cosine at 2 pi over 3 I plus 3 sine at 2 pi over 3. So refer to our unit circle, and at 2 pi over 3, cosine is negative 1/2. So I have 4 times negative 1/2 I, and sine is square root of 3 over 2. So I have 3 times square root of 3 over 2 j. We clean it up. You get negative 2i plus 3 square root of 3 over 2j. And that's our answer for that one. Okay, now to answer about the domain. As we see, for each one of the terms in our vector value function, or to be more precise, each component of them had a domain of all real numbers. So therefore, our entire vector value function has a domain of all real numbers. So our domain is all real numbers. Let's take a look at our second part of our problem. Our second problem reads r of t equals 3 tangent ti plus 4 secant tj plus 5tk. So let's go ahead and evaluate at 0, pi over 2, and 2 pi over 3. Alrighty, so at r of 0, we go ahead and put 0. We get 3 tangent of 0, I plus 4 secant at 0, j plus 5 times 0, k. Alright, tangent at 0 is 0. Secant at 0 is 1. And 5 times 0 is just 0. So we're just left with 4j. I shouldn't write secant. It's already evaluated. So secant at 0 is 1. All right, next one. R of pi over 2. So that we have 3 times tangent at pi over 2 I plus 4 secant at pi over 2 j plus 5 times pi over 2 k. All right, as we try to evaluate, we see that tangent at pi over 2, that's undefined. So because of this, we don't have an answer. It does not exist. So if we look at unit circle pi over 2, which gives us the coordinate 0, 1, 0, and 1, by creating tangent, which is sine over cosine, we get denominator of 0, which gives us an undefined value at tangent at pi over 2. Okay, next one. R of 2 pi over 3. Okay, so 3 times tangent at 2 pi over 3 I plus 4 times secant at 2 pi over 3 j plus 5 times 2 pi over 3k. Let's work it out. So tangent at 2 pi over 3 gives us negative square root of 3. So I have 3 times negative square root of 3i plus 4 times secant at 2 pi over 3 is negative 2 j, and then those are just, we can just simplify that fraction. So we have 10 pi over 3k. That is our answer for our third one. Okay, now what's our domain for this one? Notice we do have restrictions because of where tangent and secant are undefined. So if you look at what values tangent and secant are defined in our domain, we need to consider that tangent and secant are undefined at 90 degrees, so at pi over 2, and also at 3 pi over 2. So if we're measuring at every pi over 2, it'd be every odd pi over 2. Because we can evaluate at 0, pi over 2 is a problem, pi is okay, 3 pi over 2 is a problem, and back at 2 pi, which is 0, it's fine. So it's just those odd values of pi over 2. So we write our answer that our domain for r of t is equal to t such that t is now contained in 2n plus 1 over 2 pi, where n is contained in your integers. Where n is an integer. Remember, integer is just a whole number. So if you plug in an n and it's a fraction, they'll make it so that those secant and tangent values aren't defined. So we have properly defined our domain. Graphing vectored valued functions. When graphing vectored valued functions, we typically graph the vectors in the domain of the function in standard position, because doing so guarantees the uniqueness of the graph. Think back to when you wrote a vector in standard position. This convention applies to the graphs of three-dimensional vectored value functions as well. The graph of vector value functions of the form r of t equals f of ti plus g of tj consists of all the sets of t, r of t, in the path it traces is called a plane curve. The graph of a vectored value function of the form r of t equals f of ti plus g of tj and h of tk consists of all t, r of t, in the path it traces is called a space curve. Any representation of a plane curve or space curve using a vector value function is called a vector parameterization of a curve. So working with parameters along with the vectors. So let's go ahead and do an example. It's not so bad. I think it sounds way more intimidating than what it is. All right, so we're gonna go ahead and graph these three examples. We have A, B, and C. We'll do A together. I think you can do B after we do A. C is three-dimensional, so we'll do that one together. Okay, so let's take a look at A. We want to graph, or let's read the example. Create a graph of each of the following vectored value functions. A, the plane curve represented by r of t equals 4 cosine ti plus 3 sine tj, where t is between 0 and 2 pi. I don't know why I wrote a, oh, I meant to write equal. That's what that was. So when t is between 0 and 2 pi. So your book, if you look at your book, it has a way of writing your chart, which I'm not a fan of. So I'll do it the way, I'll teach you how I do it. So we have to figure out values for t. And we can pick any t we like as long as it's between 0 and 2 pi. And that's a t that we'll evaluate for, similarly to our last example. So I'll start with smaller values, so 0, pi over 4, and I think after that you'll start getting a picture of what we have. Pi over 2, and I'm going to start jumping around. 3 pi over 4, pi, 3 pi over 2, and 2 pi. Okay, now for each t, we're going to get an outcome, and this outcome would be your x and your y, which is also referred to as your I and your j for your vectors, right? And we're getting this from 4 cosine of t and 3 sine of t. So each component gets its own little box. All right, so when we plug in 0, if I plug in 0, what do we get? If I plug in 0, I get 4 cosine of 0 is 1. So I have 4 times 1, so I get 4i. When I plug it into my second term, 3 times sine of 0, j. Sine of 0 is 0, so we just get 0. Pi over 4. Cosine at pi over 4 is 2 square root of 2. Now pi over 4, it's 2 square root of 2. 2 square root of 2, and then I multiply it by 4. I have it in simplified version. Your answer should be 2 square root of 2. All right. And when you plug in pi over 4 for 3 sine of t, you'll get 3 square root of 2 over 2. You get square root of 2 over 2. Now remember. That's going to linger in my head. So this work for this is square root of 2 over 2 times 4. You get 2 square root of 2. There we go. All right, pi over 2, we get 0 for cosine. And when we plug it in for sine, we get 1. 1 times 3, we get 3. All right, at 3 pi over 4, you get negative 2 square root of 2 and 3 square root of 2 over 2. At pi, cosine is 1, so we get negative 1. So we get negative 4, and sine is 0. We get 0, negative 3, and 4, 0. All right, let's go ahead and graph this. So our t has an, how would I say? It has a direction, right? T comes from a unit circle. We're picking these values from a unit circle. A unit circle has a direction. It goes this way, right? So we'll keep that direction and those values as we go ahead and we graph. So let's go ahead and graph our vector valued function. Okay, so nothing goes above 4. I think if I do 4 tick marks on each side, we should be fine. Always label your coordinates x and y. All right, so let's go ahead and plot our points. Think of these as coordinate points. So we have 4, 0, which is here. I have 2 square root of 2 and 3 square root of 2 over 2. If you punch them in your calculator, that gives you 2.8 and 2.1. 2.8 and a bit over 2. And then we get 0 up 3. Similar to that, we get negative 2.8 and a 2.1. Then we get negative 4, 0. We get 0, negative 3. And so you can see it kind of starts skipping points at the bottom half. But you see that kind of starts forming something like an ellipse, right? This is our graph. Now, because it's a parameter, we have to include a direction. So our direction goes, you just draw a little arrow showing which way it's going. And there we have it, our vector value function. Now, I did A with you. B is almost exactly the same. So take a look at B. I think you can do that one on your own. So go ahead and pause it and get it done. Just a brief answer to your solution. It will also be an ellipse. That's exactly the same with the 4, negative 4, 3, and 3 going this way and arrows going that way. But your work is exactly the same. Let's go ahead and take a look at this 3D one. So we want to do the space curve represented by r of t equals 4 cosine ti plus sine tj plus tk. Now these examples are from your book. Your book has an error. It's missing a 4. Why do I say it's missing a 4? Because the image doesn't correspond to its question. So it's missing that 4. All right. Let's go ahead and create our chart just as before. We want values of t, and that will produce a value for your I component, your j component, and your k component. All right, we have 0. So we're starting at 0, and here it says we can go all the way to 4 pi. We don't have to stop at 2 pi. So that we have 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, and 2 pi. Okay, let's go ahead and plug in all these values. Let's begin by plugging in 0 into each one of these, and each one gets its own box, right? Just like we did before. So cosine at 0 is 1, 1 times 4 is 4, sine at 0 is 0, and a constant times 0 is 0. Pi over 2, at pi over 2, cosine is 0, so that's 0. Sine is 1, and it's by itself, so it's just 1. I think we also need a 4 here to make this correct. 4, 4, and your k is, well, just pi over 2. At cosine of 4 cosine t, we plug in pi, we get 4. Well, we get 1 times 4, we get 4. Sine at pi is 0, and pi is just itself once we plug it in for t. For 3 pi over 2, we have 0, negative 4, 3 pi over 2. At 2 pi, we get 4, 0, and 2 pi. All right, let's go ahead and try to graph it. You can continue all the way to 2 pi. I'm going to try to graph you a 3D graph, which do not hold your breath, do not bet money. It's not the best. All right, so we tend to go by 4s, right? By our formula, so we have x, y, and z. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right, so we're graphing at 4, 0, 0 for x right here. And we have 4y, and it kind of starts building up, and it kind of loses that value. So it kind of starts going like this, and it starts building upward because your z is pulling it up, and that's a horrible picture. This picture here is referred to as a helix, and because I know it would be bad, I included the picture. So this is our value, how your graph is supposed to look like. And yes, we draw little arrows because we have a parameter showing us a direction. Now again, your textbook has a typo. That should be 4 and 4. All right, limits. Everything you learn about limits translates to vectors as well. So let's begin with the definition of a limit and then continue with continuity. We now look at the limit of a vector value function. This is important to understand to study the calculus of vector value functions. So let's start with the definition, which is theorem 3.1, limit of a vector valued function. Let f, g, and h be continuous at t, then the limit of the vector value function r of t equals f of t I, g of t j, as t approaches a is given by the limit as t approaches a of r of t equals the limit of each component, which would be the limit of as t is approaching a of f of t I plus the limit as t is approaching a of g of t j, provided the limits of f of t a, the limit of t as t is approaching a of f of t, and the limit as t is approaching a of g of t exist. Similarly, the limit of the vector value function r of t equals f of t I, g of t j, and h of t k as t approaches a is given by So similarly as above, we can apply the limit to each component, each term. For each of the following vector value functions, calculate the limit as t is approaching 3 of r of t. So let's go ahead and do A. So by our definition, we have the limit as t is approaching 3 of r of t. That means that the limit as t is approaching 3 of t squared minus 3t plus 4I plus 4t plus 3j. I can apply the limit to each one of the components so that we have the limit as t is approaching 3 of t squared minus 3t plus 4I plus the limit as t is approaching 3 of 4t plus 3j. Cool. Now I can apply the limit for each one. So for this one, it's not an undefined value. We can just go ahead and plug it in. So once we evaluate, we get 3 squared minus 3t, or 3 times 3 plus 4, I plus 4 times 3 plus 3j. And so then we get 4j plus 15. Ooh, that should be an I. And there we have it. Same way for B. I think you can do B. Now that we know how to calculate the limit of a vectored value function, we can define continuity at a point for such function. So let f, g, and h be functions at t. Then the vectored value function r of t equals f of ti plus g of tj is continuous at a point t equals a if the following conditions hold. R of a exists. The limit as t is approaching a of r of t exists. And the limit t approaching a of r of t equals r of a. So these should look very familiar. Actually, these are your continuity rules from Calc 1. Just applied differently, right? Similarly, the vectored value functions of r of t equal f of ti plus g of tj plus h of tk is continuous at a point t equals a if the following three conditions hold. R of a exists, the limit as t is approaching a of r of t exists, and the limit as t is approaching a of r of t equals r of a. Alrighty, so that's all for section 3.1. Your homework is numbers 3, 5, 7, 9, 17. And as always, I like to assign the odds so you can check your answers in the back of the book or the very end of your online text. Alright, that's it for today. Thanks.